Hi students, in our previous classes we are discussing the structures of different crystals, particularly in our syllabus point of view. NaCl, diamond, cesium chloride, these main three structures are completed. After completion of these structures, we are deduce one a very good relation among the lattice constant versus density of the crystal structure. So today we are discussing about relation between lattice constant between lattice constant and density and density of the given crystal structure So for this relation you can deduce, first of all you can assume one crystal lattice. I am assuming that crystal lattice is cubic structure. The basic parameters of cubic structure is A is equal to B is equal to C and alpha equal to beta equal to gamma must be 90 degrees. So I am assuming one cubic structure. Our crystalline structure is cubic structure. That cubic structure is drawn like this. This is the cubic structure. So according to cubic structure, the end one lattice point, this is also lattice point. The distance between two lattice points can be taken as lattice constant A, and this cubic structure density can be taken as rho. Thus cubic structure density can be taken as rho. For this case, I am assuming first one I am assuming lattice constant of the given structure of the given crystal otherwise can be taken as A. Second one, I am taking number of lattice points per unit cell can be taken as small n. After that, atomic weight of the given crystal can be taken as capital M. And fourth one, density of the unit cell. Density of the cell can be taken as rho. Density of the unit cell can be taken as rho. Fifth one, Avogadro number is always be taken as capital N. Avogadro number can be taken as capital N. After that, sixth one, mass of the compound or crystal small m can be taken as, what is the mass of the compound? Small m can be taken as, you can consider as small m can be taken as capital M by Avogadro number. So this is the mass. So per unit cell, how many cells are there? How many lattice points are there? N. For n number of lattice points, mass of n number of lattice points can be taken as m by n is single atom. For n number, you can consider as m by n into n. That is the total mass of n number of lattice points. Each and every one. What is the relation among the? You can relation reduce in between lattice constant versus density. What is the basic definition of density? density always be written as mass per volume. The basic definition of density is mass per volume. Mass per volume. So, what do you take? Here you can take the structure is cubic structure. Then volume of the cubic structure. Volume of the cubic structure. Lattice constant is A. So, volume can be taken as length into breadth into height. That can be taken as AQ. That is ninth one. So, mass of the unit cell is known and volume of the unit cell is also known. So, density can be taken as mass of the unit cell divided by volume of the unit cell. So, you can substitute ninth one and seventh one in equation. In statement 9, you get density rho can be taken as mass m by n, capital M by n into small n divided by AQ. So for this relation, AQ can be taken as m small n by capital N into rho. Then A is equal to m by n capital N rho whole power 1 by 3. So m, n, capital N are constant. Then lattice constant value is inversely proportional to density power 1 by 3. That is the relation among lattice constant and density, which is very important relation for calculating the numerical values. That is a very important relation. For this calculation, first of all, what you take, cubic structure can be considered. That cubic structure condition is A equal to B equal to C. Alpha, beta r and gamma are perpendicular to each other. For this cubic structure, volume of the unit cell can be taken as length into breadth into height. That can be taken as AQ. So I am assuming lattice constant of the given cell can be taken as A, and number of lattice points per unit cell can be taken as small n. Atomic weight of the given structure can be taken as capital M, and density of the cell can be taken as rho, and Avogadro number can be taken as capital N. For basic these information, I am writing the mass of the compound or crystal can be taken as mass per Avogadro number. For n number of lattice points, so m by n into n, this can be taken as per one atom. For n number of lattice points can be taken as into n. So density can be taken as mass of the unit cell divided by volume of the unit cell. So mass of the unit cell and volume of the unit cell can be substituted in this equation. M by n into n, then divided by AQ. So lattice constant A can be written as m by n by Avogadro number into density into whole power 1 by 3. So m value, n value and capital N value are constant. Then relation among lattice constant and density is always be inversely proportional. Particularly lattice constant is inversely proportional to 1/3 of whole power density power 1/3. So density is increases, lattice constant value is decreases. So here the distance between two lattice points is increases, density of the material is decreases. That is the main relation among the lattice constant versus density. A is inversely proportional to rho power 1 by 3. That is the main relation among the lattice constant and density. So this is the main relation among lattice constant versus density. So each and every point step by step I am explain. You have any doubt, please call to me. Each and everyone knows my phone number, please call. So once again I am repeated because that video has some blurred images are there. So each one note down clearly. First of all, lattice constant can be taken as A, number of lattice points can be taken as small n, atomic weight can be taken as capital M, density of the cell can be taken as rho, Avogadro number can be taken as capital N. So based on this relation, you can take the mass of the crystal can be taken as atomic weight divided by Avogadro number. This is for one atom. For complete atom can be taken as for n number of molecules, n number of lattice points are there. For n number of lattice points, n into m by n. So according to density basic definition, mass by volume, mass of the unit cell divided by volume of the unit cell. So here we are taking the cubic structure. The cubic structure is A equal to B equal to C, alpha equal to beta equal to gamma equal to 90 degrees. So based on this relation, volume of the cubic structure can be taken as length into breadth into height. Length, breadth, height along x, y, z direction, lattice parameters always be equal. According to our calculation, you can take the lattice constant is A. So A into A, that is A cube. Substituted in this equation, finally you get the relation. Lattice constant A is equal to capital M small n divided by capital N rho whole power 1/3. So according to the topic is relation between lattice constant versus density. Here I am taking the lattice constant is A, density can be taken as rho. So A and rho relation is inversely proportional. So atomic lattice constant is inversely proportional to density. Particular relation is A is inversely proportional to rho power 1 by 3. A is inversely proportional to rho power 1 by 3. Otherwise, it is also known as or A cube is inversely proportional to density, which is also the correct. A cube value is inversely proportional to density. A cube value is inversely proportional to density, which is the best relation among the lattice constant versus density. This relation is deduced with respect to crystal structure. Up to this point, the crystal structure, based on crystal structure, topic is completed. So crystal structure topic up to this one. So from this point of view, we can go to the next topic. Nothing but particularly with respect to lattice planes. We are going to the next topic based on lattice planes. So first of all, you can note down step by step. Okay, completed. So up to this topic, we are completing the crystal structures. From this topic ending onwards, we are going to the next major topic based on lattice planes. So lattice planes also we are completed in past classes. Basic definitions of crystal. We are completed basic definitions of crystal. On the topic we are explaining the lattice planes. What are lattice planes? So each and everyone just recall it. What is a lattice plane? Each and everyone recall it. What is a lattice plane? So first of all, you must know the topic is lattice plane. What is lattice plane? Before going to the lattice plane, you can know the lattice. Actual lattice is nothing but space lattice. Actual lattice is nothing but space lattice. Space lattice can be expressed in three-dimensional point of view. What is three-dimensional point of view? Lattice is nothing but crystal structure. Crystal structure is nothing but periodic array of lattice points. Periodic array of lattice points. This is called as crystal structure. This crystal structure is explained or expressed in terms of three-dimensional point of view, nothing but x direction, y direction, z direction. So the three-dimensional point of view, this lattice points arrangement can be expressed, that is called as lattice, especially space lattice. After that, what is a plane? What is a plane? Plane is expressed in three-dimensional point of view. X, y, z coordinates are there. those depending on their coordinate axis according to geometry, you can draw the planes. In two-dimensional planes also you can draw based on two-dimensional point of view. Plane need only two coordinates, either x, y, otherwise y, z, otherwise z, x. This is the two-dimensional plane. In space lattice, we can explain the plane in terms of three-dimensional. In three-dimensional point of view, you require three-directional coordinates x, y, z. So, lattice points can be explained in three-dimensional point of view. That plane is nothing but particularly lattice plane. According to the periodical structure of lattice points can be taken as like this. I am showing the dots. This dot is nothing but lattice point. So periodical arrangement of lattice points arranged like this. I am showing either 5 to 6 rows. Why I am taking 5 to 6 rows? In this structure I am showing different lattice planes as you wish. I am showing different lattice planes, approximately 3 to 4 lattice planes I am indicating. So I am taking, this is the lattice or periodical arrangement of lattice. So I am taking the lattice planes. A plane passing through the lattice points, a plane passing through the lattice points like this. Like this. These are the lattice planes. So these are the horizontal lattice planes. So I am taking another one. This is the first one. Second one, vertical lattice planes. I am showing like this. These two also lattice planes. This is the second one. This is the horizontal lattice planes. This is vertical lattice planes. I am showing the z direction also like this. This is also a lattice plane. Lattice plane. I am showing one more like this. These are the lattice point. I am showing the lattice plane in terms of triangular form. So that's it. This is one more lattice point. This is also. So that is the fourth type, that is can be taken as triangular lattice points. Suppose I am taking one lattice point like this. This squares also indicating lattice planes. In this way we can showing different lattice planes. The separation between successive lattice planes can be taken as D. Can be taken as D. This D indicating interplanar distance. Interplanar distance. Sound even? Interplanar distance. This interplanar distance is equal. Suppose this is also D. So this plane 1, plane 2, plane 3 are parallel planes. If D is same, those planes are called as parallel planes. The interplanar distance between the two successive lattice planes are equal, then you can maintain same distance. Those planes are called as parallel planes. So parallel planes is nothing but the interplanar distance between two successive planes is always be constant entire the structure. So that is the lattice planes. You can draw the lattice planes in different point of view. This D distance is indicating the interplanar distance. Very important. So if distance D is equal, those planes are called as parallel planes. Here I am drawing the 5 types of planes. One is parallel planes, second one is perpendicular planes, third one is also perpendicular along z direction, fourth one is triangular planes, fifth one is square planes. Otherwise you can take circular planes also, you can show it. But these are the different types of lattice planes. So based on this lattice planes, we can introducing a new term that is called as Miller indices. That is the present topic. For this topic, the introduction is mainly based on lattice planes. What is lattice plane? Lattice is nothing but space lattice. Space lattice is nothing but you can express the lattice points in three-dimensional point of view. So that's crystal is nothing but periodical arrangement of atoms. This periodical arrangement of atoms can be represented in three-dimensional point of view. The entire structure can be taken as crystal or crystal structure. In this crystal structure, you can pass the one lattice point according to the lattice plane, passing through the lattice points, then the plane is called as lattice plane. So in between two successive lattice planes, there existing some distance. The distance can be taken as interplanar distance. If the distance between successive lattice planes, you can maintain the same distance, same interplanar distance, those lattice planes are called as parallel lattice planes. Those planes are called as parallel planes or parallel lattice planes. Based on lattice points or lattice planes, we are introducing a new quantity or new term that is can be taken as Miller indices. That is the main topic after completion of crystal structure. So present topic is Miller indices. Each and everyone knows Miller. What is the name of Miller? Generally each and everyone knows Miller is nothing but a scientist, especially physics scientist. Miller name is the scientist name. He introduced some indices. Based on this. Miller introduced how to represent lattice planes. Miller introduces how the lattice planes are represented in crystal. So that how to represent the lattice planes are based on Miller indices. So what is the meaning of indices? Actually indices is nothing but intercepts. Miller indices is nothing but intercepts. How intercepts are gained? You get the intercepts along the three-dimensional coordinate axis. Three-dimensional coordinate axis nothing but space lattice. In the space lattice, we can introduce a lattice plane. What is the lattice plane? The plane passing through lattice points. Then the plane is called as lattice plane. This plane is introducing in three-dimensional point of view. The three-dimensional point of view indicating is lattice, indicating based on Miller indices. So Miller indices are used to represent the lattice plane in three-dimensional point of view. That is the main part of Miller indices. How the Miller indices are gained? Generally, in our practical point of view, Miller indices are indicating by letters H, K, L. These three are small letters. H, K, L are the Miller indices. Particularly lattice planes are indicating in terms of curved brackets. In between the letters there is no need of comma or colon anything. So Miller indices are indicating by letters H, K, L within curved brackets. So this curved bracket indicating this complete structure is indicating A lattice plane, a lattice plane in the crystal. A lattice plane in the crystal. So in the crystal you can represent the lattice plane by using the three letters H, K, L. Those are included with curved brackets. That curved brackets indicates Miller indices. How the Miller indices are getting? So these Miller indices can be getting by step-by-step process. By using step-by-step process, we are going to take the example. So you can clearly explain step-by-step process. First of all, note down. This is the major introduction point about Miller indices. So we are going to the next topic, that is the Miller indices. Up to this point of view, we are completing crystal structure. In our crystal structure, what are the topics mainly completed? Particularly in crystal structure, major topics. First topic in our crystal structure. We are completing first of all basics, otherwise definitions. Definitions are completed. After completion of definitions, we are going to the types of crystals. Types of crystals in a crystalline and amorphous, those properties. After completion of types of crystal, we are going to the crystal systems. Totally how many systems are there? 7 systems. These 7 systems is representing or easily remembered by C. Tom is a teacher. He teaches Hindi. So total 7 structure based on their lattice parameters, nothing but A, B, C according to their axial length A, B, C and alpha, beta, gamma are their axial interfacial angles. After completion of crystal structure, we are going to the Bravices lattices. Entire Bravices lattices in the crystal structure is totally 14. Based on these 7, you can convert it into different internal structure. So those are mainly repeated: simple cubic, face centered cubic, body centered cubic, base centered cubic, and fifth one, body centered cubic. Simple cubic is simply called as primitive cell. Face centered cubic is represented by capital F. Body base centered is represented by I, and body centered is represented by B. After completion of Bravis lattices, we are going to the calculation of number of lattice points per unit cell. Number of lattice points per unit cell. Particularly for simple cubic structure, only one lattice point. Face centered cubic structure, totally 4. Body centered cubic structure, they have 2 lattice points. After completion of this number of lattice points per unit cell, we are going to the packing factors. Packing factor density, simple cubic structure is 54%. Face centered cubic structure is 74%, and body centered cubic structure is 68%. At this condition, we are going to the diamond also. Diamond is only 34%. So weakly bounded structure is only diamond. So after completion of this, we are going to the structures of NaCl, second one cesium chloride, third one diamond. This diamond structure is also similar to zinc sulfide. NaCl structure, it is a combination of 2 FCC structures. Cesium chloride is a combination of 2 simple cubic structure. Diamond structure is also combination of 2 FCC structure. Zn is also combination of 2 FCC structure. After completion of this structure, we are going the relation among the density and lattice constant. So A cube is inversely proportional to 1 by D. Otherwise, this is also is represented by A is proportional to 1 by d power 1 by 3. This is the main points regarding in crystal structure. Based on this crystal structure, you are completing complete main topic crystal structure. After completion of crystal structure, we are going to the another topic that is called as Miller indices. Miller indices mainly indicating the lattice planes in three-dimensional point. So Miller indices is indicating by letter H, K, L. Particularly these are representing small letters. In between the letters there is no need to indicating commas or colons anything. These three letters are indicating in curved brackets. These curved brackets indicating the Miller indices, nothing but which indicating the lattice planes. After completion of this one, we are going to how the Miller indices can be calculated, how they can draw the lattice planes based on Miller indices. This topic can be continued in our next class. So up to crystal structure, each and everyone knows. You have any doubt, please contact my phone number 9912520005. This is our standard phone number which is belongs to both WhatsApp and phone contact. So this is WhatsApp and phone contact. You have any doubt, please contact and feel free to clarify your doubts. Okay, each and everyone must complete it up to crystal structure. Tomorrow onwards we are discussing Miller indices, how the procedure to calculate or to get the Miller indices. Based on Miller indices, how to draw the lattice planes in the crystal three-dimensional point of view. Tomorrow class we will discuss only Miller indices.